FRC robot, and then Zach Gerlin will be covering the different kind of robot propulsion systems. Zach is the co-captain for Robot 17 and 11 team this year, and he's been in it for 4 years now. So, with that, we'll go ahead and switch over to the electronics presentation, if I can find it. Most of you probably have had some exposure to this, I assume, if you've had a robot in the field. Your basic core components. The top there is your robot reel. That obviously has your program in it. That's the brains of the system. You've got your radio up here on your left. You've got your VRM and your PCM on the right there, which is the pneumatic control module and the voltage regulator module. Pneumatic control module feeds a signal to the compressor on and off, as enabled by the robot reel. The voltage regulator module just regulates voltage down to the right voltage. You got your PDP here, which is your power distribution panel. Basically breaks out your incoming voltage for your different circuit branches. Always remember to keep in mind you have 12 gauge for your larger breakers, and you do a smaller gauge cable on your other breakers. Some else, the other components here are some drives hooked up in here for your different drive systems. This is just a document that goes through and builds a board with the power distribution panel and all the other components on it. Kind of gives you some hints as you go through. There's the main circuit breaker, so your battery feeds one side of this, and then this goes over to your PDP on the other side. And this will cut all power to the robot. This needs to be in a very accessible place. So us as robot inspectors can say whether or not it's accessible. It's kind of a gut call, but you don't want that tucked to the middle of the robot. Basically, it is a safety component, and if there's a fire in your robot, you want to have somebody go walk up to that robot and kill all the power to it so that it doesn't feed that fire. So that's being located on the outside, well accessible if you can. It doesn't need to be hanging outside the robot, but it needs to be accessible from the outside of the robot. Oftentimes I'll see these loose in competitions. If you're experiencing a lot of brownouts with your robot reel, one of the main causes is loose slugs on the PDP or loose slugs over here. Very common to see that. So you want to make sure you tighten those, snug those up real well, and you shouldn't be able to grab this cable and move it at all. It should be really firm and no relative motion between these components. There's a typical wiring. Battery coming in this side routed over to PDP, and then battery ground coming into here. Any questions on it? You always want to see tape on those lugs because, as you can imagine, this incoming wire here is going right to the battery. So if a piece of metal should fall on this and it's grounded to the robot, you're going to end up with a short and a fire. So we're going to be looking to see those covered up with some electrical tape, typically red electrical tape on the red side and black electrical tape on the black side. It goes with wires to cover these as well. In place you've got exposed main lead wires. Typical PDP hookup, there again, maintaining your 12 gauge wires up here and your 40 amp breakers. Your sub breakers down here could drop down to 16 or 18 based on your breaker size. There's a spark controller for your motors. Your power out here. These are typically labeled up on these components. Most of the time you can read them. Eyes get older like I am, you can't read so well, but they're all labeled. These are power outs to your VRM here, looks like your PCM here, power into your robot reel card there. There's your VRM power coming in. Kicks out 5 volts from your 12 volt signal. You may want to use that for cameras or switches or whatever takes the low voltage. You guys pretty familiar with this, or any questions? Yeah? All good stuff? Alright, so we'll kind of fly through it fast here. Pneumatic control module, I don't know how many of you used that. Raptors just used it last year, first time in many, many years. But basically you've got incoming power, your CAN bus in here needs to be hooked up, and then you've got control to solenoids coming out here, and compressor control coming out there. So you can control up to 8 solenoids on that thing, or 4 double solenoids. Radio and Ethernet power. We are recommending anymore that you use power over Ethernet for your radios. There's a little power connector over here, and it just doesn't stay in place. So the PoE injector with radio power is a much better and more secure way to go.
You learned that a couple years ago.
Yeah. Hard lesson to learn.
Yeah.
Talked about that. CAN bus, anybody any questions on CAN bus? How else should have it hooked up? Usually use green and yellow wires. So your CAN bus connections. Robot signal light, that dude's got to be visible from the outside. I've seen some robots that didn't have it visible from the outside. Don't tuck it down inside and cover it with a bunch of stuff. Have it out. There again, as inspectors, we're going to be looking for that. That's going to be flashing in sequence with your robot reel bulbs. So we're looking for that connection to be strong. That's a good sign. If it's not, if it's out of sync with that robot reel, then something else is going on with your CAN bus usually. There's your 40 amp circuit breakers. When you're putting those in the PDP, make sure you push down real hard. There can be a real bugger, so you got to put quite a bit of pressure on those to lock them in place. That's really all I have to say.
That connector you have back there?
This one here.
Oh, there's a couple slack back.
The yellow one?
Yeah, we have some of those and we haven't used them.
Have not used these at all?
No.
These are helpful when you want components that are replaceable. For instance, if you're putting an auxiliary motor or something on your actuator mechanism, and you want that thing to be replaceable real easy, we'll put a splice in the line just so we can pull it apart, just replace the motor, pop it back together, and we'll splice both ends of the spare motor. So that's typically where I'd see those. You're not really going to want those on your main power line or anything like that. It's usually used in an auxiliary motor combination.
And it goes off on the PDP.
Yeah, a branch circuit somewhere. Good question. Obviously, you're really going to want to have your chargers all set with these connectors anymore. We're not allowing any chargers without those types of connectors in buildings. Just keeps the positive polarity thing going on with your battery and your charger. So typically carry a spare or 2 of those around. That's really about it for the electronics side. Any questions? Okay. I'm going to invite Zach up, and he's going to talk about propulsion.
Do you got any fun?
Yeah.
So, hello, my name's Zach. I'm the technical captain for Team 1711. I was build lead last year. So I found this presentation about drivetrains, kind of how to choose them, what they are, when to choose what, how to kind of rank them. So yeah, if you have any questions, just kind of interrupt me. So the purpose of a drivetrain is kind of be like, it's the most important subsystem of your robot. Without it, you can't get around the field to complete the game objectives. So you have to be able to traverse what can be some difficult obstacles. You have to be able to, it must be durable and reliable. So it's the most important thing, and probably the most time worthy that you should use. So before we get into the drive systems, I'm going to talk about a couple types of different wheels. So I have brought a couple out. So we have your traction wheels, which are just kind of your standard normal wheels. They'll come in your kit of parts. You can get them on Andy Mark or X Pro. Also kind of in the same category, your new Attic tires, which are just these but with air in them. They come at varying amounts of traction. There's nothing really special about it. They're just your kind of standard wheel. Omnis, we are actually using all of ours currently, so I don't have an example of those. But they have rollers around the outside of them so that they allow it to go forward and backward and side to side. So it allows it to slide pretty
Just
easily.
out of curiosity, when running those on a drive, are they powered through a belt or no? Are they just standalone bearings?
They
Completely
can be.
different thing?
It depends on what type of drive you're running. Last year on Daedalus we did have them powered. We we had tractions in the back and omnis in the front. What omnis allow you to do is, so when you turn, you'll turn from the back because that's the things that hold, and then you'll turn on your omnis because they're the things that let you roll side to side. So that kind of went well with our back heavy robot. So you can combine them with traction and omnis. You can do all omnis. You just have to be careful about being pushed around a lot. You don't have a lot of traction with them. So yeah, that answers your question. Okay. And then, kind of along the same lines as omnis are mechanums. So they're almost like omnis, except the rollers are attached at a 45-degree angle. Also allows for multi-directional motion. They're more efficient, I'd say, but they tend to be slower in drive speed. So they give more traction, but
So like for the omnis, can you not go side to side and forward at the same time? Like you can't go diagonal?
well, they actually don't add any driving force side to side unless you are running like an H drive or something. So your really only method of using the omnis is when you turn, it allows you to roll better on the ground, which makes it a tighter turn if you're using all omnis. So they're really good with pairing with like tractions, so that you can turn on a pivot almost. Whereas mechanums, when they're set up right in the right configuration, allow for strafing movement. You can go diagonally, you can go back and forth. You are liable to be pushed around by other robots, so they're not great for defense, and they do tend to be slower than most other wheels. Kind of the positives and negatives of mechanums. So getting into a couple different types of drivetrains. First you have the tank, which is kind of the most common you'll see, the most standard. So you'll have 2 rows of wheels that are driven independently. They typically come in sets of 2. You tend to see either 4 or 6 wheel drives, so 2 and 2 or 3 and 3. So there's a lot of strengths to tank. It's simple, it's easy, you don't have to put a lot of thought into it. If you do it right, it works well, pretty reliable. It actually puts out a pretty consistent pushing force, and so it's not bad for defense at all. It is slightly less agile than other drivetrains, which is something that you have to look out for if you're working within tight corners or you need high mobility. But it's really not that much of a downside. So swerve or crab. So you'll have wheel modules that rotate independently of each other. Crab is like swerve. I don't know how much research everyone has done into swerve. Swerve has separate modules that work with two motors, one to turn it and one to make it go forward, allowing for programmers to program in using calculus and being able to kind of go wherever you want depending on which way the joystick points. Crab does almost that sort of thing, except it works with it makes the modules dependent on each other, so they'll all rotate as one using chain, as you can see here. They chain them to motors, so they all rotate as one and all drive as one.
So it's like shopping cart wheels.
Yes, exactly.
Have you tried those yet? Or?
No, they're almost harder than swerve to build. They don't tend to be very durable.
Programming the pain.
Yeah, they kind of are a hassle to deal with. So strengths about swerve and crab. So there are some. It provides as much pushing force as traction wheels would, or tank wheels, if you're going straight, because they're all going to be pointing in the same direction. And it's more agile than a tank drive, because you can make very, very tight turns. But some of the weaknesses, they're very complex, very expensive to build. For swerve, you're looking at a minimum of 8 motors for your drivetrain. Extra motors to rotate the robot frame. Most teams that undergo swerve, it's a multi-year process. So there's a lot of work that goes into swerve, and it's not necessarily worth its benefits. But there are some pros to swerve and crab. So slide and H-drive, I call it H-drive most commonly. It's a similar layout to a tank, except you have an extra wheel that's in the middle of your system, which allows for side-to-side movement. So this is where you could run all Omnis and get the full benefit, is when if you have full Omnis on your sides and then an Omni in the middle, you can run the Omni in the middle to go side to side, to strafe, as well as going back and forth with your two on the outsides. So the strengths of this one is it's fairly easy and cheap to build, just a little bit more than a normal tank, as you would think, and it's more agile than a tank because you have that strafing mobility. Some weaknesses is you have no potential for high pushing force unless you're going directly into something else, and you can be pushed side to side very easily, and even up and down. You don't have very much traction there. It does require an extra hub. It requires an extra wheel set, which requires its own motors, its own gearbox. So there is a little bit more that goes into it. But yeah, it does give you that strafing mobility. So, yeah. And then Mecanum. So Mecanums are, they lay out like tank. You must use Mecanum wheels. And you must lay them out correctly in the right orientation in order to get the full benefit. So the strengths are, it's pretty easy to design and build. It's almost the same as a tank drive, except you're locked into a 4-wheel drive system. It's agile. You are able to strafe, go at a 45. You're able to go forward, backward. Some of the weaknesses, though, are you again lose the potential for pushing forces because you're working with rollers on the outsides like Omnis. It's challenging to program.
When it came to this year, some people were talking about when it comes to a ramp pod, for example, going up that ramp, they were not able to with the with these wheels.
Yeah.
So I'm assuming, say you're at an angle, you just slide back down due to the rollers.
That could be an issue. Yeah, I would think that it would be more of an issue of your drive speed and how low to the ground the robot frame was.
Okay.
Mecanums drive slower than other drive systems. So if you're trying to go up the ramp and you go up the 15-degree incline, I think it's a 15-degree, and your robot frame is too low to the ground and you don't have enough pushing force or speed to get over the hump and kind of rock yourself onto the ramp, then you're beached. So I would assume that would be the problem with it.
If I could add something to that discussion, the Mecanum wheels rely on like a transverse friction to move. Because they have the external rollers on them, you're basically driving one roller against the other to provide forward motion. If you lose that friction like you would on the ramp last year, then you don't have any friction to drive you side to side, and that loses your thrust entirely.
Okay.
So you need friction, you need carpeted friction almost to have macadams work.
So it wouldn't work on as well on like bumpy terrain like Stronghold?
Yeah, correct.
Okay.
Correct. Yeah, so some of the weaknesses about Mecanum, you lose the pushing force because of the traction and because of the potential for being pushed around. It's challenging to program. I believe there's some calculus involved in programming it. And to learn how to drive well, I think there's a little different controller scheme when you're driving it. The wheels are more expensive than just normal traction wheels, and you don't get them in kit parts. So there's a couple more steps that you have to go through in order to build Mecanum for a more agile robot. Okay, also there's holonomic drive. You don't nearly see this one as much. But you have 4 Omni wheels positioned 45 degrees on the edges of the robot. Each wheel has to be driven independently, or driven independently. So it's more agile than a tank drive. I wouldn't say it's more agile than a Mecanum or an H drive. It's not exactly durable. There's a lot of things that can go wrong while building holonomic drives. You lose the potential for your pushing force, again, because you're working with all Omnis. You can be pushed around very easily. It requires extra gearboxes because they all have to be driven independently. You can't chain them to each other. So yeah, you don't really see holonomic a lot, but there are times. Okay, so he kind of moves into how to choose one drivetrain over another based on maybe your team experience or what the game is this year. So if you get the numbers get a little convoluted, so just kind of stay with me. But so yeah, each drivetrain has its own strength and weakness, so you really want to pick the best one for the game and what you want to do. So yeah, the different drivetrain attributes that you want to compare. The main one is agility, being able to move around the field. In 2016, being able to get over the obstacles. In 2019, being able to kind of position yourself in order to get the balls inside of the cargo and the rocket. So a lot of things that kind of go into that. it's almost, unanimously the number one kind of thing that you need out of a drive system. Another attribute is your strength. You have to be able to push game pieces or robots if you're playing defense. You have to be able to resist defense from all sides. If you look at an all-Omni tank drive, it's very susceptible to being pushed on the side, and then you'll just kind of drift away. So you have to be able to be sturdy enough to stand your ground in some games, and you have to be sturdy enough to push other robots around in some games. And also your number of motors, because the motor limit is limited. So you don't want to be using more motors than you have to. Like how in Swerve you need 8. A normal tank drive uses 4. So you can save twice your motors by using a tank drive over a Swerve drive. Programming. So ideally you won't have something that requires a ton of programming if you don't have experienced programmers. But again, Swerve, Mecanum, you start getting into calculus, you start getting into higher maths in programming, and being able to rotate the modules at just the right amount so that they go where they need to go. You don't necessarily want to be using sensor feedback. It just kind of overcomplicates your drivetrain. So yeah, for an example, the wheel module angle, which is what I was talking about with the Swerve drive, knowing how far to turn the wheel before it goes forward and backward. You want it to be easy to drive, because your drivers will most likely not get a ton of time with the robot. So you want to have it be intuitive to control. You want to have the ability to move sideways, but you don't necessarily need it in some games. And you need to be able to traverse obstacles, kind of the whole agility thing. But being able to go over bumps and steps. And finally, the design considerations. So you have your cost, you have to know how easy it is to design, manufacture, assemble, maintain, repair, and you also have to look at the weight of it. So I mean, Swerve typically weighs a ton more than just a tank drive would. Or custom making your tank drive, other than taking just the one that you get out of the kit of parts, can save you some pounds here and there. When you have a limited amount of weight, that can sometimes be really crucial. So those are all things to kind of, he categorizes them, and then he weights each of the drivetrains against the system. So he puts up a table here, out of 1 to 5, the number of motors, agility, strength, programming, driving, traversing, and designing. So this is kind of like a set ranking based on what you might want to do based on the game. What you also have to think about while thinking about this is you have to think about your strategic analysis on the game, your priority list, what you want to go for, and also what resources your team has. So you want to rank those on a 0 to 10 scale based on how important you think they are to the game. And so yeah, like your agility, if you don't think it's important, you'll give it a 0. If you think it's important, you'll give it a 10. Design's kind of the big one. It's a lot based on how many mentors, students you have, how much experience you have. Obviously, if you're a rookie team, you don't want to be building Swerve. What tools are available to you? If you can't manufacture the parts for Swerve, then why are you building it? How much money do you have? A lot of the things cost more money than a tank drive would. Mecanums are pretty expensive. So sometimes that will go into your considerations. So you want to rank that on 0 to 10. So a typical weight for rookie or low resource team. So they're obviously ranking the agility, strength, and number of motors as a 5, right in the middle. Their programming and ease to drive and design, which they think they'll take the most, are 10s. And they don't really know how to traverse the obstacles or what the strategy is really, so they'll give it a 0. So that's kind of like a basic kind of weight system for a low resource team who might not be able to accomplish many of the game's tasks and look to just kind of play the game. So yeah, so then the next step is taking it and putting it into the table and multiplying it out, and then you divide your the number that you get by the total, and you'll get a percentage. And based on that percentage is the drivetrain that this presentation suggests. So yeah, it kind of goes through rookie, average, strong team. He kind of ranks them how he feels fit. And so almost unanimously with this method, you get a tank drive, which it's simple, it's cheap, it's easy to make, and it does the job. And that's kind of what you're looking for in a drivetrain. So if you are always getting tanked, then why would you choose another one? So that's kind of what this goes into. When to choose a swerve drive? If you have a large team, you have many resources, and you're kind of out of stuff to do, your kind of next step is going into swerve or going into something that's more complicated, something that will kind of challenge your kids in the off season. Like we're doing right now, we're kind of prototyping a swerve drive. That will probably take us many years. But yeah, you have to have a large budget, you have to have the ability to be able to manufacture all the parts, assemble all the parts. Not lots of students and mentors that are involved. It's a big process to build swerve. When you choose slide, when agility is equally as important as reliability. So if you don't have an agile robot, is that going to lose you the game? That might be when you choose swerve or slide over a tank drive. So yeah, mecanums, kind of the same thing. When strength is not required and you kind of need a more precise movement, that's when you might choose mecanum drive. If you have a strong programming ability, if you have the resources to do it, if you've used mecanums in the past, so you have the wheels, that would be when you can do it. So yeah, I think.
Any questions on the weighting table? Everybody understand that?
Good. Okay. So now we start getting into like kind of the technical things about drivetrains. So your speed reduction, you don't want to gear your robot too high, where it won't have enough torque to move. You don't want to gear your robot too low, where it goes super slow. So normally a good robot speed is about 8 to 12 feet per second. Some can go quick, some can go quicker, some can go slower. So there's a lot of ways to change your reduction. You can do it in the gearbox. You can change, if you're using sprockets, you can change the pulley or the sprocket size to make it a 2 to 1 or a 3 to 1 even. So yeah, you can really change that however you want to, but you want to make it so that you're not going too slow and you're not going too quick. It's kind of the Goldilocks right at the right movement speed. Yeah. So wheel size selection. So your smaller wheels will give you less reduction needed. It's less weight, which is a big one. Wheels weigh a lot. They can weigh anywhere from half a pound to a pound, and you have at least 4 of them. So that's a good weight saver if you can cut off a pound or 2. Your large wheels will give you lower RPMs for the same distance. So just kind of things to think about there. Principles that apply to this. Yeah, so that's not what you want to do. But yeah, so the big one is your center of gravity, right? Something that a lot of teams had to deal with last year was how to get onto the tier 3 or even the tier 2 without having your robot tip over. And that deals directly with your center of gravity, which you really want to be really low and in the center of your robot. The more it's like that, the less likely your robot will be to tip, and the better your robot will handle. So accelerate and turn. So yeah, the bottom line is that it dictates how much force each wheel provides to move the robot. So if you have a back heavy robot, your back wheels are going to be moving the robot more than your front wheels, right? So you might tip backwards if you're a back heavy robot, kind of thing. Yeah, so if your center of gravity passes the point of no return, then you'll fall forward and tip. So that's what you want to avoid by making your robot low to the ground, as low as you can get. Yeah. So getting into like tank drives specifically, there are actually a lot of different types of tank drives. They mostly depend on the number of wheels and the number of motors. So tank drivetrains have pairs of wheels, and the left and the right wheels are driven independently. However, you can have a 4-wheel drive system, you can have 6, 8, even 10 wheels. And that will kind of improve your maneuverability over obstacles. Our robot last year, we started with a 4-wheel tank drive system, and then realized that we couldn't get onto the ramp, and so swapped to a 6-wheel tank drive system, which allowed the middle wheels to contact when the back and the front 2 couldn't, and so then we were able to get up there no problem. So yeah, in 2016 you saw a lot of 6 or 8-wheel tank drives that would be able to traverse the defenses pretty easily.
What's going on with that thing?
What?
What's going on with that one?
Yeah, so I think this one was more for show, but you can see there is, I think, 10 or 12 wheels on that one. And they'll all be driven by a set of motors, whether it's 2 sims that you put in a gearbox, or a sim and a mini sim, or whatever it happens to be, a Neo.
Wouldn't have your pushing battle. You could never get pushed.
Yeah, so it gives you greater traction, which is always good. Yeah, so the real advantage to a 4-wheel drive system is it's less weight. You're saving the weight on the wheels, you're saving the weight on the pulleys, the extra motors that you may have to use or not. Disadvantages would be, if your center of gravity is skewed, sometimes the turning is a little iffy, where you might have your thing kind of jitter as you turn, which can be solved by adding omnis or whatever. 6 wheels, so it gives you the full pushing force while making sure that you aren't getting pushed on the sides if you're using all traction. It does add weight, and it's not great at traversing some types of obstacles. So even with 6 wheels, there are still ways that you can get stuck on some obstacles, which you just have to be aware of. Yeah, so that's all I have.
Are there any benefits to adding even more wheels than 6, or does it just kind of stop?
Well, it's more of the same almost. As you add wheels, you get more places of contact. So you'll get stuck less often. If you can think back to 2016, going over the like different sized rectangular prisms. The more points of contact you have there, the less chance you'll have to get stuck on it. But I mean, anything over 8, I don't think you'll see very much benefit to.
So it's just kind of law of diminishing returns.
Yeah.
Can we get copies of the presentation or?
Yeah. I actually have, I have one that has this presentation and it has like 5 other presentations. I can give that to you as well.
We also are taping this for tonight, so we'll put that online as well.
Yeah. So, any other questions? Awesome. Well, thanks all for coming.
Thank you for having us.
Yeah.